This is the screencast for section 2.2, example 3. The title of the example is Using Theorem 5. Way to give you absolutely no reference of what this is about. So let's talk about Theorem 5 first. Theorem 5, you don't even need to know it by Theorem 5, that's just what your book called it. Properties of limits as x approaches positive and negative infinity. Now these properties are the same as we studied in section 2.1, just now as x approaches positive or negative infinity. So you can still add two limits together, you can subtract two limits, multiply by a constant. You can divide as long as the denominator doesn't approach 0, etc. So let's look at an example. Find the limit as x approaches infinity of 5x plus sine of x all over x. Well, there's no way I'd be able to do that just as it's written, so I'm going to take the numerator and split it up over the denominator and break that into two limits. 5x over x simplifies to 5, so the limit as x approaches infinity of 5 is going to be just 5. But now I have to find out what this part's going to be. Well, I'm going to rewrite that, and I've got another sandwich theorem situation. I'm not going to make you do that sandwich theorem again. This is a limit that you may never forget at this point. The limit as x approaches infinity of 1 over x times sine of x. It is a good one to memorize. You'll see it in a lot of trig limits as x approaches infinity. So that does approach 0. If the directions ask you to use the sandwich theorem, you should be able to do that. But if they don't, you can just say that that's equal to 0. So the limit is 5. The now try problem number 25 says y equals the sine of x over 2x squared plus x. And we're going to find the limit as x approaches positive infinity and the limit as x approaches negative infinity. So I'll do the limit as x approaches positive infinity first of sine of x over 2x squared plus x. Well, this isn't like the last problem in that I can't break up the addition sign in the denominator, but I can factor out an x in the denominator. And yes, I know it's annoying that you have to write the limit as x approaches infinity every time, but you do, so deal with it. The limit as x approaches infinity now, I can see the sine of x over x here, which is good, times, and then I can do separately the limit as x approaches infinity of 1 over 2x plus 1. So I know that this limit is 0, so it doesn't actually matter what this limit is because 0 times anything is going to be 0. But when you think about it, as x gets infinitely large, the degree in the denominator is bigger, so this is going to be 1 divided by a really, really large number, also going to approach 0. So your limit as x approaches positive infinity is going to be 0. Now let's look at the limit as x approaches negative infinity. I'm going to start where I left off with this problem, with the step the limit as x approaches now negative infinity of sine of x over x times the limit as x approaches negative infinity of 1 over 2x plus 1, because those first algebraic steps would be the same. So now I have to think the limit as x approaches negative infinity of sine of x over x. Well, I know that sine of x is going to oscillate between this function here is going to oscillate between y equals 1 over x and y equals negative 1 over x. So again, by the sandwich theorem, it's still going to approach 0. Now the limit as x approaches negative infinity of 1 over 2x plus 1. Well, if I plug in a negative number that gets bigger and bigger and bigger, 1 is still going to be divided by a really large number, which is still going to approach 0. The values are going to be really tiny negative values this time, so like negative 0.0001, negative 0.00000001, etc. Limit is still 0 though, so I still have a 0 limit as x approaches negative infinity too.